Okay, we're doing the proofs topic, and this is a really big topic, proof by induction. It's a really versatile proof. We can use it in a whole range of mathematical areas. Induction means to kind of lead on, to take along with you, to induce us to a process of persuasion. In a way, we're going to persuade that something is true for, if it's true for what we call the nth term, what we want to do is to say, okay, if it's true for the nth term, I want to show you that it's true for the very next term, n plus 1. So if it's true for one term, all we need to do is to prove it's true for the very next term, n plus 1. So the logic is that if it's true for n plus 1, then it must be true for the next term, n plus 2, and so on. So in other words, all we're doing is we're saying if it's true for this one, it must be true for the next one. And we get this little line of dominoes. I've got a wee picture here. Okay, so here's our line of dominoes. And if we say, okay, imagine that, or we're going to assume that the process or this conjecture is true for the nth term, what we want to do algebraically is show that it's true for the next term. Okay? Now, if we then refresh our situation, if we then say, well, we know it's true for the n plus 1 term, and therefore we've shown that it's true for the very next term, then it must by definition be true for the n plus 2 term. But we've shown that if it's true for one term, it's true for the next one. So, in other words, it's true for the n plus 3 term. So we've got this little domino stack that says, basically, we've shown that it's true for the next one, but then it must be true for the next one, and then the next one. The only problem is, where does it start? Well, it has to start at the first term. And as long as we can then prove that it's true for the very first instance of n, it might be n equals 1, for instance. If you can prove true numerically that it's true for n equals 1, then you're saying, well, if n is 1, then it must be true for n equals 2. But if n is true, if n is 2, and we know it's true for the next one, then it must be true for n equals 3, and so on. And in toppling the first domino, we're able then to topple every domino to infinity. All by saying that we know that if it's true for n, then we've proven it true for n plus 1, the next term. Okay? So there's a little bit of, you got to get your head around that, okay? So that's just a wee illustration of the fact that as long as we can topple the first domino, we can then topple them all. Right, so what we're going to do is, this is oddly enough, well, this is the structure of proof by induction. So we're trying to establish a proof for all values for all n, okay? And we do this by basically checking that it's true for n equals 1. You can do this at the end, but I tend to do this at the beginning. In other words, we set up an initial step. Let's set up our first domino. Is it true for n equals 1, for instance? Usually 1, but you might be told it's not. Okay, prove that it's true for the first one, and that's your first domino. And then what we do is we create what's called the inductive step, and that is that we have to make an assumption that it is true. Assume true for n equals k. So we're going to then define whatever the formula, the conjecture is. We're saying, yeah, okay, assuming it's true for n equals k, what we then need to do is to prove true for n equals k plus 1. And what you're going to find is, see all these statements here, we're going to actually write these in our proof as well. So you're going to find that as a script. You're going to algebraically show that it's true for n equals k plus 1. And then we have this logical argument, which is basically our summary that we're going to write down at the end. And it's pretty much a script. We can effectively, it would be good if you could understand it. We're saying that if it's true for n equals k, then we're showing that it's also true for n equals k plus 1. There's your dominoes. Because it's true for n equals 1, then k plus 1 has to be 2, and then 3 and 4. In other words, we've shown that if it's true for n equals 1, it must be true by induction for all values of n. Okay, that's the structure of it. We'll come back to that in a moment. But before we actually go into our first example, I want you to highlight the fact that sometimes in our proofs, and we're going to start with these types of proofs, we're going to use summation statements. And so there's a little bit of theory we need to tackle here. So let's have a look at this expression here. The sum of the first r terms from r equals 1 to the number k plus 1. Okay, we're basically saying that's whatever all the numbers say, it's 1, 2, 3, blah, 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 up to the k plus 1th term. Well, we know that what must be the true is that it's the sum of all the values up to k, that's k, the kth term, plus whatever that k plus 1th term is, the actual expression k plus 1. So we can say that the sum of terms up to k plus 1, we can break that up into 2. That's the sum of all the numbers so far, which is the sigma up to k plus 1, up to k rather, plus the actual value, what you get when you put k plus 1, what is the k plus 1th term in the formula. It's another way of saying, for instance, if I want to add to get, say, the first 10 terms, okay? Say I wanted to find the sum of the first 10 terms. Then it's equivalent of saying what we do is it's the sum of the first 9 terms plus the 10th number, which has to be 10. Okay, the sum of the first 9 terms is 45, and of course we know that the sum of the first 10 terms is 55 anyway. Okay, so it's a way of splitting up a summation into 2 parts. Let's have a look at this one here. So if we're given, that's me just kind of highlighting what we're just doing there. Given the fact that the sum of the first 4 terms is 10, then the sum of the first 5 terms is going to be the sum of the first 4 terms plus what happens when you put 5 into the expression r, which just gives us 5. We know that that's 10 plus 5, which is 15. Okay? Let's have a look at example 17. So this is not proof by induction, we're just trying to use this summation expression. Okay, so given that the sum of the series 2r plus 1 from r equals 1 to k, given that we know that the total value of that is k squared, find an expression for the sum of the first k plus 1 terms of 2r minus 1. So what we're saying here is that we can split this up into the sum of the series 2r minus 1 from r equals 1 just to k, the first k terms, plus what happens when we take k plus 1 and substitute it into the expression 2r minus 1. And what we get there is 2 lots of k plus 1 minus 1. Okay, that's the last term in the series. We already know, because I've just been given it over here, that the sum of the first k terms is k squared. So in other words, I can substitute that for k squared. I can then multiply out this to get plus 2k plus 2 minus 1, and the expression that I get is k squared plus 2k plus 1. Okay? So what I'm going to do is I'm going to leave that there. I'm going to start then example 18, which is the first proof by induction example, just so that it's not quite so long. So go and watch example 18 and we'll see that structure of the proof that I've just given you actually into practice, and we're going to use what we've just done here with the splitting up the summation of k plus 1 terms. Okay, check it out.